Assalamualaikum and good day everyone. We are student Principal Control System Section 1G under Dr. Dwi Febrianti. Today we want to present about our project assignment which is Sunseeker Solar System. Before that, I want to introduce myself and my other group members. My name is Nur Amira Shafika binti Saleh, EA 18024, and the second member is from Oika, EC 17073. Then the third one is Jordan Leong Tatpao, EC 17076, and the last one is Wan Nur Bidayatul Hidayah binti Wan Azizan, EC 18076. So let's start our presentation.
To Madam, my name is Jordan. Today I will present about the extract. This report is the summary and result of the assessment tool with the title of the driver or modeling analysis and designing a controller for one of the industry application regarding the mechanical or electrical system under the subject of the BEE 3313 principle of control system. This report is present the design of the Sunseeker solar system as the choice. PID controller used in the Sunseeker system due to the simplicity of control structure, robustness, and wide range of application. The three constants in the PID controller algorithm may be tuned to give control action designed for the various process need. Addition of the derivative of to the Sunseeker solar system reduce the proportion of the overshoot.
So I will continue this presentation. I will explain about the introduction. In this project, we have been given the task to propose the suitable modeling of the Sunseeker solar system and need to employ any of the controller design technique. We are using the Simulink MATLAB software to design the proportional integral derivative PID control system to discuss the open and closed loop performance of the Sunseeker solar system and also to reduce the proportion of overshoot. The Sunseeker system is a component of altitude control that is frequently required to correctly direct a spacecraft high-gain antenna to Earth for communication. The most popular type of feedback control is the PID controller. To create a complex automation system, it is frequently paired with logic sequential function selector and basic function block. Each of the three control modes of the PID controller, proportional, integral, and derivative, react differently to error. After that, KP stands for the changeable setting or control gain for proportional control. Then as long as there is any mistake, the integral control mode raises or reduces the controller output over time to reduce the error. Ki donates the gain for integral control. So this is the block diagram of a Sunseeker system where it has error discriminator, operational amplifier, controller, server amplifier, DC motor, and also have the feedback back EMF. For this one is a transfer function of the Sunseeker system where Ks is equal to gain of error discriminator, Ki is a torque constant, K is a gain of server amplifier, Kb is back EMF constant of motor, La is armature inductance, Ra is armature resistance, and the last one is A over N is a gear train ratio. That's all from me. Hidayah will continue our presentation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I am Wanu Biditri Abidu Azizan. Okay, for this assignment, I will explain about the methodology. Firstly, find the article that relate to our title, which is Sunseeker Solar. Then, based on the article, we modified the block diagram for closed loop and open loop. Then, the two panels were created using the equation below, as the physical system consists of two major components. The first is the motor, while the other are for the velocity. The equation and model for the velocity panel and motor panel. Then, this is the the equation and model for the velocity panel. 7. The equation and model for the motor panel with derivative. Then 8. The model for the motor panel without derivative. And 9. The Sunseeker solar closed loop model with PID controller. 10. And lastly, the Sunseeker solar open loop model with PID controller. Okay, this is the step in the modeling process. First, setting the step blocks. Then, use the summing point at the closed loop and remove the summing point for the open loop. Then, add the transfer function with equation that was provided in the journal article. Using the tools code to measure different blocks. Third, combine the subsystem for the motor panel and the velocity panel. Observe the result before and after improvement. Then, lastly, this is the step in the controller process. Create a motor subsystem by using gain KF and KG configuration. After that, create a velocity subsystem gain KD with two integers. Add the derivative block to motor subsystem for improvement. That's all from me. Thank you.
Okay, I am from Aika EC17073. Today I will present about the result analysis for this assignment 2. So firstly, we will look at the case 1 cross loop without derivative. This is the graph that we get from the scope 1. Means in each case they got two scope, and here got scope 1 and scope 2. So the result that we get, the overshoot is above 10% at time without derivative. Means if there is no derivative, means derivative drop won't have occurred at here. So the second one is it also from the case 1 cross loop without derivative, but it from the scope 2. So this is the graph. Then at here shown the overshoot still above 10%. Then the case 2 is the cross loop derivative. So at cross loop derivative here, they got one derivative block which is at here. So we can see at here the overshoot for uh, this cross loop derivative model is below 10%. While the next one is it also from case 2, but it's cross loop derivative. This one is from the scope 2 derivative block, still same derivative block, but the waveform is from the scope 2. So the overshoot still below 10%. So at here we can see case 1 without derivative is overshoot is above 10%. Case 2 cross loop got derivative, but overshoot is below 10%. For case 3, this is now is about case 3 is open loop, no derivative. But just now is cross loop. So what is the difference between cross loop and open loop? First, cross loop got feedback and summing point, while the second one, the open loop, is no summing point, no feedback. So this is the graph that our group get from scope 1 and scope 2. So for this graph, there is open loop, no derivative. So we can see it here, the overshoot, pre-shoot, undershoot, there is no value. Same with here, the graph from scope 2, also same, there is no value. While the case 4 is open loop derivative. So now the open loop got derivative at here. So here, pre-shoot, overshoot, undershoot, also same. There is no any value here from scope 1 and scope 2. So for the discussion part, like I explained just now, by comparing the performance for open loop and cross loop Sunseeker system, it was determined that cross loop outperform the open loop system and can be, then the cross loop is suitable used for Sunseeker system. This is because open loop system is compatible with our Sunseeker system with a PID controller, as I demonstrate just now by case 4, case 3 and case 4 result. So a better Sunseeker produce a sinusoidal signal, not a linear signal. The result indicates that a cross loop with a derivative has a lower shoot percentage than a cross loop system without a derivative block. So as a result, a lower overshoot indicates a good and stable signal. From the case 3 open loop, no derivative, we can see the graph that from scope 1 is nearly linear but a slight overshoot. Then the graph from scope 2 and the case 4 open loop derivative graph from scope 1 and scope 2 is linear signal graph. So I guess that's all from me. Next, about the conclusion and reference part, I will pass to my partners, which is Jordan. He will explain about it. Thank you.
Okay, as a conclusion, we have successfully developed a model of the cross loop and Sunseeker solar system. For the second one is the objective was accomplished through the application of our knowledge of the control system principles. We used a derivative block to control the rate of the change of the error in the current model of the Sunseeker solar system. Okay, we also able to achieve a more stable and improvement performance of the Sunseeker solar system with a PID controller by the implementing this derivative block. Thus, the knowledge of the control system principle accurate throughout this semester enable us to apply this project through the use of the controller design technique. Okay, this our using for reference for the Sunseeker solar system. We're using the 4 journals. Okay, we just choose the 4 journals for the reference and do the project. That's all for me. Thank you.